kind of talk through it like we did last time.
Okay, Systematic, this is our video for lesson 6. So number 1 is asking, well, 1A asks, what's the frequency of the D allele in this population? Let's see, and they give us the number of individuals that are affected by the disease is 1 out of 150,000. So 1 out of 150,000 is our Q-squared number. So the square root of that is D, or is the frequency of the D allele, which is 0.0026 or 0.256 or 26%. Fix that. Okay, and then B, what is the frequency of the D allele, of the big D dominant allele in this population? Well, if you just take 1 minus your Q value, or your D allele frequency, I have too many decimals on that answer. So 1 minus 0.0026 is 0.9974. And then what's the frequency of the homozygous dominant genotype? So that would just be the D squared value. So 0.9974 squared gives you 0.9948. And then what is the frequency of the heterozygous big D little d genotype in this population? So that's going to be 2 PQ, or 2 big D frequency times little d frequency. And I still have too many decimals here. You got 51. 0.0051. And then moving on to question 2 with the fill in the blanks. Determine the Hardy-Weinberg equation that represents the frequency of the IB alleles. Of the IB allele is Q, while the term in the Hardy-Weinberg equation that represents the frequency of IAIB genotype is 2PQ. And then DiGeorge syndrome is an autosomal dominant disorder that affects 1 in 4,000 individuals in the population. The 1 in 4,000 individuals in the population affected by DiGeorge syndrome is represented by the P squared and the 2PQ because it's dominant. So both the homozygous dominant and heterozygous individuals will be affected. And then C, this question refers to the situation presented in Part B. 3,999 in 4,000 individuals in the population is unaffected by DiGeorge syndrome. This is represented by Q squared because it's the homozygous recessive individuals. And then for D, we said that the R term in the Hardy-Weinberg equation represents the frequency of the MD allele because there's 3 alleles that have that are for plumage, and so the last one we said was R. And then E, the question refers to situation in D. The P squared plus 2PQ plus 2PR terms in the Hardy-Weinberg equation can represent the genotype of a duck with restricted plumage because restricted plumage is the most dominant. And so if it has that allele, it will express it. And then the human disease sickle cell anemia is the result of a SNP. And G, monomorphic is a term that describes a trait that produces a single phenotype in 99% or more of the population. H, DEEM is another name for a local population. And I, the MHC genes in humans are highly polymorphic.
So for 3, we're talking about the Marfan syndrome, which is autosomal dominant. And so we're given that it affects 1 in 6,000 people. So what we did was just to find the recessive one, which is 599 out of 6,000, which ended up giving us a 0.99992, or after that's squared,
Yeah, so
or square root of that.
Mhm.
Yeah. So whatever the heck this number was,
you just square root the fraction.
and then that gave us 0.99992. So that ended up being our Q value, and then we subtracted that from 1, giving us as our P value. And then the frequency of heterozygous, right? You just multiply these guys and then times by 2, so it's 2PQ for heterozygous. Ended up being 0.00016. And then for out of the 5 million people, how many heterozygotes are there? Just times this by 5 million, and that gives us 800 people. Down to number 4. Thank goodness we got this up.
Yeah. Okay, so for number 4, they gave us the frequency of genotypes. I think I have it. Yeah, there. And so we just made like a little table that helps us know how many of each allele is present in an individual with a particular genotype. So it says determine the allele frequency of R2 and R3. Well, there are 135 individuals that are homozygous for R2. I don't know if it says dominant or recessive. It doesn't. They're homozygous for R2, and so each one of those individuals has 2 of them. So 135 times 2, like 270, or 2 times 135. And then there are 44 heterozygous individuals, so each of those has 1 of both. So they input 44 of the R2s and 44 of the R3s. And then for the homozygous R3s, there are no R2s in them, but there's 2 R3s per individual. So it's 2 times 11, 22 R3s. And then there are 190 individuals in this population, and each one of them has 2 alleles for this gene or for this trait. And so the total number of alleles in the population is 2 times 190 is 380. So you just take the total number of R2 alleles divided by the total number of alleles. That gives you your P, and that is 0.8263. And then you take the total number of R3s, divide that by your total allele count, and that gives you your Q, and that is 0.1737. And then we did our chi-square. Basically, in order to find the expected number of individuals that should be homozygous for R2, we took the frequency of R2, squared it, and then multiplied by the total number of individuals, which is 190, and that gives you 129.73 is the expected homozygous R2. And the expected heterozygous is 2 times PQ, or 2 times the frequency of R times the R2 times the frequency of R3, and multiply that by the total number of individuals. That gives you 54.54 expected heterozygous. And then the expected homozygous R3s is frequency of R3 squared, so 0.1737 squared times 190, and that gives you 5.37. So you put that in the chi-square equation, and the observed individuals that are homozygous for R2 is 135 minus the expected, which is 129.73. Square that and then divide that by 129.73. Take that number and add it to the other parts of the chi-square, which is the observed minus expected squared over expected. And our chi-square value ended up being 7.09. And since the degrees of freedom are only 2, that doesn't fall within the acceptable range. So we said that for part C, we said that the chi-square value is too large. So this population is not in Hardy-Weinberg equilibrium, which means that, and the reason why is that they are undergoing evolutionary change. And this is the last one now.
All right. And so for part 5, it is asking what is the frequency of the chinchilla colored that is homozygous for that. And we went through and did the calculation for that. So we took the 0.37 and we squared that to get a 0.1369. And then for the second part of that one, it is asking for the CB C, and so we did that. We took 2 times the 0.25 times the 0.15, and we got 0.075. And then for part 3, we wanted the homozygous recessive or CC on that, and we took 0.15 and squared that and got 0.0225. And then for part B, we were wanting how many among a population of 2,000 dogs, how many would you expect to have the pale gray phenotype yet be heterozygous? So for that, we took the 0.075 value that we got above for the CBC, and we times that by the 2,000 and got 150 dogs. And then part C, among a population of 5,000 dogs, how many would you expect to have the white coat with dark eyes phenotype yet be heterozygous? And so that one, there's 2 different possibilities to do that. So we took the 2 times the 0.23 times the 0.25 and then added that to the 2 times the 0.23 times 0.15. And then we multiplied all that by 5,000 and got 920 dogs that would fall within that range. That would have the white coat with dark eyes. And then part D, among a population of 15,000 dogs, how many would you expect to have the chinchilla with the CB or the CC genotypes? And so we took the 2 times the 0.37 times 0.25, added the 0.15 squared, and then multiplied all that by the 15,000 and got 3,112. And that is everything.
All right. I'll see you next week.